Hello and welcome, everybody. If you don't know me, I'm Paula Hammond, and I'm the Department Head of Chemical Engineering at MIT. And I'm really happy to have you here today with us as we launch our new Chemical Engineering Virtual Seminar Series. While we wait for everyone to come in, I'd like to say a few words, and then I'll give an introduction to our speaker, one of our youngest faculty members. But first, let me give you a little bit of an update about what's been going on in the department. First of all, I'm glad you're all safe, and we've been keeping safe here as well in this really incredible and unusual year. You may have heard that we had to close our campus down during the spring, and probably for a period of about 3 to 3.5 months, we were at very minimal, if any, research at all, but we had a gradual ramp up during the summer and ultimately ramped up to what is closer to a 100% but spaced capacity in September. And during that time, I'm really proud of the way that our faculty were able to come to the forefront of teaching remotely. Our students and their roles as TAs and researchers in lab really did fantastic things anyway. And we continue to keep the spirit of the community alive and going. So things are actually going very well. And with that, I'd like to add a list to our link to our website in the chat. And that's going to give you a little bit of information about what's been going on in our efforts in the department on COVID. So just a moment to brag a little bit. We are incredibly proud of our colleague, Bob Langer, who is the academic founder and one of the scientific advisors of Moderna. And that is, of course, the Moderna whose coronavirus vaccine is on track to be approved for emergency authorization within the next 24 hours or so. And we think it's a truly stunning accomplishment that we have an mRNA-based vaccine that is going out to patients and to the American public. At the same time, Chris Love is one of our faculty members who's been working on developing an incredibly low-cost recombinant subunit vaccine, which has the potential to be deployed into areas without developed medical infrastructure, which is incredibly important to really address the issue of COVID around the world. He's one of the Gates Foundation partners, and he has been using one of his developments in rapid development of vaccines, and they've already seen that there is an immune response, and one of these proteins has now been incorporated as a product candidate in clinical trials. So we're very excited about that. Along with that, Hadley Sykes has been working on rapid paper-based tests, and Greg Rutledge has been working on testing mask efficiency and tested the entire N95 stockpile of the Massachusetts Emergency Management Agency. We also have projects that are going on in therapeutics, in transmission modeling, and in other areas. And I'm hoping to highlight some of this work in the seminars that we have coming out this spring, as well as in our newsletter. Now, while 2022 has been a profound disruption, one of the upsides is that we've all become familiar with Zoom and all of its versions. Many of you haven't been to campus recently, but this is a great opportunity to bring all of you back as alumni to campus to see what kinds of exciting research is going on in our programs. And I want to say that we really appreciate the depth of technical and academic accomplishment of our alumni, as well as of our faculty. And this is a chance for us to showcase that in these seminar series. I'm really excited to introduce Kartish Mantiram, who is our inaugural speaker for this chemical engineering series. So I'd like to give you a few biographical points on Kartish. He is one of our newest members of the department. He joined us in 2017 as the Theodore T. Miller Career Development Chair. He got his bachelor's degree at Stanford. He went on to get his PhD from Berkeley. He worked with Paul Alivisatos, who's a very well-known academic in the area of nanomaterials. And he then came to us after doing a postdoc with Robert Grubbs at Caltech, where he developed new anion exchange ionomers. I'm going to let Kartish explain his own work, but one of the things that gets me most excited is his principle of being able to generate synthetic molecules using the simplest and most abundant of the molecules on Earth. And I think this is one of the really big ideas in sustainability and environmental chemistry. Now, Kartish has been accumulating an impressive number of awards in his career, and that includes the NSF Career Award, the Department of Energy Early Career Award, and the American Chemical Society New Investigator Award. Kartish was named as one of the Forbes 30 Under 30 and one of AICHE's 35 Under 35. So he is essentially one of the rock stars of chemical engineering. He's also been recognized as an incredible teacher, and he's actually won the Michael C. Moore Undergraduate Teaching Award and the Chemical Engineering Outstanding Graduate Teaching Award, both of which are awarded by the students themselves. He also recently won the MIT Teaching with Digital Technology Award, and I think you'll see why today. It's my real honor to introduce my colleague, and I'm really looking forward to hearing this talk today. So welcome, Kartish.
Awesome. Thank you, Paula, for the very kind introduction. It's really fantastic to get to spend this snow day interacting with our alumni. I think there's really no better way to spend it. So thank you very much to all of you for spending this time with us. So I'd like to start by putting up this image and asking, where is the carbon footprint? And I think instinctively, we might point to the gasoline-powered vehicles or to the electricity powering the lights. But there is, of course, a carbon footprint behind virtually everything that we see in this image. There is a carbon footprint behind the plastic of the billboards, behind the clothes that everyone is wearing, behind the cement of the buildings, the steel of the flagpoles, and behind the patty of the McDonald's burger. These carbon footprints are inescapable. So we can look in here to quantitatively see where this carbon footprint is. The industry that generates these chemicals and materials is responsible for 33% of global anthropogenic greenhouse gas emissions. So clearly this is an important problem to tackle. We can hone in on the chemicals part of that. And here we plotted the greenhouse gas emissions of the top 18 commodity chemicals. And you'll see something very important here, which is that there is one chemical, ammonia, which has such a large carbon footprint that it in fact has its own y-axis. It's separated out because if ammonia didn't have its own y-axis, all the other chemicals here would be compressed down at the bottom of this plot. So ammonia has a carbon footprint of 350 megatons of CO2 equivalent. This is an enormous CO2 footprint. So if we're serious about decarbonizing the manufacturing of chemicals, we need to find a way to decarbonize the production of ammonia. So one thought that might cross your mind is, well, why not just reduce the amount of ammonia that we make or work towards stopping ammonia production? But this, of course, isn't possible since that ammonia is used in so many essential applications. This ammonia is used as a fertilizer for growing foods. It's used as a disinfectant. It's used to produce fabrics and plastics. So there are so many applications that we count on in our everyday lives that we would rather find a way of decarbonizing that ammonia production so that we can continue to use it in these essential applications. So the way that we make ammonia today is in what we call the Haber-Bosch process. In this process, we start with methane and water, and we react both of these at greater than 700 degrees centigrade to generate hydrogen. Now here we're taking these oxygen atoms, placing them on the carbon so that we can rip off these hydrogens to make this hydrogen. And what that means is that we generate a stoichiometric CO2 footprint. And this footprint then is why ammonia has the largest CO2 emissions of any chemical that we manufacture today. We then take this hydrogen and we react it with N2 from the atmosphere to make ammonia. And we do the second step at 400 to 500 degrees centigrade and 150 to 250 bar. So there are two major problems here. The first I've already mentioned, that's the CO2 emission that we see right here. And the second is that these conditions are relatively harsh. This is chemistry that you can't do in your garage. These temperatures are sufficiently high and the pressures are sufficiently high as well, such that this can't be done in a distributed manner. There are large benefits to doing this sort of thermochemical reaction in a centralized fashion, which is how it's practiced today. So this here is an image of a Haber-Bosch plant in Germany, which probably cost on the order of $2 to $3 billion to build. That ammonia is made there in a centralized fashion and then distributed out to the world. And we'll talk later in this presentation about why this centralized model has not allowed us to get fertilizers to everywhere we need them in the world. But we can lay out at least two goals at the beginning here. One is to eliminate that CO2 footprint, and the other is to find more benign processing conditions such that we could eventually enable distributed manufacturing of ammonia. So our vision for doing this is to develop an electrically powered process. To start with CO2 and nitrogen, which could come from air and from exhaust gas, and to combine that with water. And these feedstocks then can be combined using renewable power at 25 degrees centigrade and 1 bar in order to generate diverse chemicals and materials. So we can take carbon out of CO2, take nitrogen from dinitrogen, hydrogens and oxygens from water, and combine these 4 elements, carbon, nitrogen, oxygen, and hydrogen, and stitch them together to make many of the chemicals and materials that we rely upon in our everyday lives. So we could generate fertilizers, make paint, make carbon fiber, and make fabrics. These are some of the early targets that we're approaching in our laboratory. So this here shows how one might actually implement this paradigm. Imagine that you have a solar farm, which is generating large amounts of cheap renewable electricity. That renewable electricity could be fed, for instance, to a neighboring plant, which can take air from the atmosphere, take water from a neighboring source, and react those two to generate ammonia. So this is the basic reaction that we're showing at the top here. The only externality here is oxygen. So rather than making CO2, which is what we get when we use methane as the hydrogen source, by using water as the hydrogen source, our only emission here is of oxygen, which of course is benign. We could hopefully do this at 25 degrees C in 1 bar and with renewable power. And that ammonia that we make could then be used to fertilize a neighboring field. So you can see here how this is a paradigm that enables the generation of this ammonia close to where it's needed. So what we've put forth so far is that we want to replace pressure with voltage. And let's see what this means in the context of this specific reaction, this reaction of nitrogen plus hydrogen going to ammonia. So we can start with the thermochemical case. This is a color map that shows the conversion of this reaction. The conversion is defined as going from 0 to 1. If it's 0, it means we're entirely at reactants. And if it's 1, it means we've fully gone to product. So regions which are red are favorable thermodynamically, and those which are blue, we would try to stay away from. So looking at this thermodynamic map here, we may perhaps want to start at close to room temperature and ambient pressure. And what we would find, of course, is that while the thermodynamics are favorable, the kinetics do not work out. These collisions do not lead to productive conversion of nitrogen and hydrogen to ammonia. So we're forced then to increase the temperature, going up to say about 500 degrees centigrade. And at this point, the nitrogen and hydrogen kinetically react, but thermodynamically, we can see on this plot the problem, which is that we have a near 0 conversion. So while this is kinetically useful, it is not practically viable due to thermodynamics. So we can then pressurize this reactor, take it up, say, to 200 to 250 bar, and at this pressure, achieve a slightly lighter shade of blue, where we have about a 15% single pass conversion. And this is how we make all the world's ammonia today. It is remarkable to me in a way that this is how we feed the world, with a process that has a 15% single pass conversion. And really, it's a testament to engineering that we've been able to make this work as well as it does. So we can consider then an alternative possibility, which is to use voltage in the place of pressure. If we replace the y-axis of pressure here with voltage instead, you'll see a very different thermodynamic landscape. So let's say we start at 500 degrees centigrade, and instead we apply voltage. You'll see here that we actually cut across these contours. And that's what's very special about voltage, that with just 1/3 of a volt, one can get to a point where there is greater than 99% conversion. So with voltage, with just 1/3 of a volt, we can do more than what we could have done with hundreds of bar or even thousands of bar of pressure. And that really is what's special about voltage. It allows us to take linear excursions through free energy space, whereas with pressure, we find that we're applying more and more pressure, but we're simply following the contours. So voltage allows us to cut across contours, while pressure simply follows contours. And this, at the very heart of it, is one of the advantages of using electricity to shift chemical equilibria. Now, a second aspect which is important is that the voltage helps not just the thermodynamics, it also helps the kinetics. So in principle, we could operate at a lower temperature. And realizing this advantage is what our lab has been focused on, to use electricity and to find catalysts that can make this vision come true. So we've been working on a lithium mediated route for nitrogen fixation. And this development of catalysts is important because the previous plot may have given you the impression that this should already be possible. But the reason why it's not, and the reason why it's not already commercially deployed, is that we don't yet have catalysts that can facilitate this electrically driven transformation of dinitrogen gas into ammonia. The hardest part of that is breaking the nitrogen triple bond. And here we're using lithium metal to do that difficult step. The lithium metal reacts with N2 in order to generate lithium nitride. This is a reaction which happens at ambient conditions. So it's something that doesn't really require much effort on our part since the lithium is doing the heavy lifting. This lithium nitride, which contains separated nitrogen atoms within it, is something that we can then protolyze, so we can break this apart, generating ammonia and regenerating lithium ions. So this is done by the introduction of a proton donor, which here we leave generic as just HA. We'll define that in just a moment. These lithium ions then are replated, making lithium metal, and then we can continue around the cycle. So this has been shown in various ways in the literature, even before we got started in this area. I show one example here of a batch-wise process. Here, one starts with a molten lithium chloride, lithium hydroxide bath, plates out lithium ions to make lithium metal, scrapes that lithium metal off, making a lithium foil, cuts this up, puts it in a beaker, adds in nitrogen gas to make lithium nitride, then drip in water to make lithium hydroxide, along with ammonia, and then boil the ammonia off, leaving lithium hydroxide behind, and then put that lithium hydroxide back into this first vat here in order to plate the lithium back out. So while this acts as a proof of concept in the literature, we know, of course, that this is not going to be a viable method of making the ammonia that the world needs. This is a multi-step process conducted in batch, and with this sort of solids handling, that would make it very difficult to practically implement. So there's one other report from the 90s showing how with 2 electrodes immersed in solution shown on either side here, with bubbling of nitrogen gas through an electrolyte containing lithium perchlorate and THF with ethanol, one can plate out lithium ions to make lithium metal, have that react with the nitrogen gas here to make lithium nitride. That lithium nitride can then be protolyzed by the ethanol, which is the proton donor, making ammonia. And that all of this happens in a single vessel. And so we were really inspired by this prior study, but recognized its limitations, that there is a Faradaic efficiency of just above 8%. This quantity, which is very common in electrochemistry, means that only 8% of the electrons that were going into the system were going towards the desired chemistry of making ammonia. The other 92% were going towards other undesired reactions. So a Faradaic efficiency gives us a way of doing electron-based accounting. So it's simply an electron-based selectivity in the system. And the rates were also relatively low, so 0.55 nanomoles per centimeter squared per second. So these are a relatively humble starting point in terms of an electron-based selectivity and the rate with which ammonia was being made. So we set out then to try to achieve higher rates and efficiencies for a semi-batch nitrogen reduction process. And we wanted to do this by elucidating the mechanism of this reaction, which before had not been uncovered. So I show here an example of the reactor we used in our early studies, which involves a copper cathode and a platinum anode, an electrolyte with lithium tetrafluoroborate and THF with ethanol. And what's really neat here is that if we zoom in on the cathode, all these processes are happening simultaneously. At the surface of the copper electrode, We're plating lithium ions to make lithium metal. We're transporting dinitrogen to the surface, which reacts to make lithium nitride. That lithium nitride then reacts with a proton donor to make ammonia, and that ammonia is then evolved. And all these microscopic steps are occurring at the same time at the surface of the electrode. So I want to show just one example of the sort of kinetic data that our lab likes to gather, which we couple with a wide range of other kinetic data and spectroscopic experiments, but showing just one example here. So this plot shows that we measure, for instance, the log of the partial current for ammonia. So that's the current that actually goes towards producing ammonia as a function of the overall current that's applied to the system. And there are two regimes that emerge here, one which is kinetically limited, which our group identified, as well as a transport limited regime right after that. And so we've been able to separate these two and learn to describe the kinetics that occur in this region through a vast array of kinetic experiments that we've done coupled with spectroscopy. So I won't show you all the other data here, but I do want to show the outcome of that, which is the ability to write a reaction network. We can see how one starts with lithium ions. Those lithium ions then are plated to make lithium metal. That lithium metal can then go to one of two fates. One is reacting with dinitrogen to make lithium nitride, which then eventually leads to ammonia. Or this lithium metal can be intercepted by the proton donor directly, making hydrogen. So this then is our undesired reaction. We want to avoid making hydrogen from this lithium and instead promote the generation of ammonia. So our lab developed this understanding of this reaction network by writing very simple rate expressions of the sort that many of you probably learned in 1037, and taking these simple rate expressions and combining them along with boundary layer theory. So using our knowledge from 10302, which is the course that I actually teach, so it's something that's near and dear to my heart. But putting together then this kinetic description of the rate along with a transport correction, which we were the first to recognize, which together then allow us to quantitatively describe the Faradaic efficiency, or this electron-based selectivity for this reaction. And what we found is that this is a problem that the field's been trying to solve for 2 decades and was stuck at around a Faradaic efficiency of about 8%. And with this model, which unveiled the kinetics and the mechanism of the reaction, in a single experiment, we were able to double the Faradaic efficiency from 8% to about 18 to 19%. So a significant improvement in the selectivity, and also increase the rate to about 10 to the minus 8 moles per centimeter squared per second. But what was important here is that we could continue to try to make better catalysts that could operate at faster rates, but we were limited by transport. And this meant that transport would continue to mask any improvements in the catalyst beyond what we had achieved here. So we knew that we had to make a new architecture for this reaction. So we have two problems then. So the first, which I just described a moment ago, is this issue of transporting nitrogen from these bubbles to the surface of the electrode where it's needed. So we have an issue of transport. And the second is that we have an undesirable proton source in this reaction. We're actually oxidizing THF and ethanol at the platinum anode. And while this allows us to study nitrogen fixation at the cathode, I think we can all agree that chewing up THF and ethanol to make ammonia is something that's not going to be techno-economically viable. So our group sketched this out on a whiteboard about 1.5 years ago, just dreaming of how we would want to fix this reaction to overcome these two problems. The first was that we needed some effective way of contacting this gaseous nitrogen with the liquid phase electrolyte and our solid phase here, which brings in the electrons. So we needed some new contacting scheme. And we also needed to introduce hydrogen at the anode such that our overall reaction would be nitrogen plus hydrogen goes to ammonia, instead of nitrogen plus THF and ethanol going to ammonia plus undesired oxidation products of THF and ethanol. So this cartoon sketch we thought could help overcome these challenges. So we developed this new technology in our lab, which involves a metal mesh electrode. This metal mesh electrode allows us to contact the nitrogen gas with the liquid phase electrolyte and the solid electrode. And this system then involves this sort of architecture, which you can zoom in on and look at in a scanning electron microscope. The stainless steel cloth we can directly employ at the cathode of the reactor. And we can also deposit catalysts on it like platinum, which can enhance the rates of hydrogen oxidation at the anode. So this same metal mesh can be used both at the cathode and the anode of this reactor. So what we find in our experiments is a dramatic enhancement of the rates and Faradaic efficiencies. So I show here rates of about 30 nanomoles per centimeter squared per second. So this is breaking the previous transport limit that I described of 10 nanomoles per centimeter squared per second. So we're already seeing rates that are above what we could achieve in a flooded system. And beyond that, we see that the Faradaic efficiency is also much higher. We can reach a Faradaic efficiency of 40 to 50%. So we're well beyond what was the prior record in the field of 8.5% before we started, or what I showed earlier in our own lab of around 20%. So we're putting about half our electrons now towards the desired process. We can also couple this to water splitting. So of course, this isn't just about taking nitrogen and hydrogen and reacting those to make ammonia. We want that hydrogen to come from water splitting so that it is from a sustainable source. So here we couple this to an electrochemical water splitter. And we can see this on the right-hand side. This is the actual prototype that we built in our lab, which then allows us to realize this overall reaction of water plus nitrogen going to ammonia plus oxygen. We can see how this stacks up relative to what's been shown in the broader literature. So all these data points shown down here in green and in red and in blue and in purple are all the best performing data points from the literature, which are plotted based on their Faradaic efficiency on the x-axis and the production rate on the y-axis. And you'll see here that the system that we've developed with these two black points have much higher rates, 1 to 2 orders of magnitude greater. Certainly there's room to improve in the Faradaic efficiency, but the rates are essential for capital equipment depreciation. So this is a system which right now holds the record for rates of ammonia synthesis at ambient conditions, but we're of course looking to continue to improve upon this. So the big problem in this system, which I haven't talked about yet, is that while we've solved in part the problem of rates and have improved the Faradaic efficiencies, we're losing a lot of energy in this system. So at present, for all the energy that we put in, only about 3% of it goes towards our desired product of ammonia. And what this means is that we need to do energy accounting to figure out where all the other energy losses are. And it turns out that most of them are from resistive losses in the electrolyte. We're wasting a lot of energy trying to move ions around in the electrolyte. So we're initiating efforts in our lab, and this will likely be a multi-year effort to actually solve this problem, to develop new electrolytes. So first, we want to be able to create an architecture which is thinner, simply by reducing the distance between the electrodes. That can reduce the resistive losses. So this is one important effort that we're undertaking in our lab. And a second, which we'd like to also work on, is to make more conductive electrolytes. By switching out the solvent and the proton source, we can reduce those resistive losses and head towards making a system which hopefully has an order of magnitude higher energy efficiency. And we think at that point, this could actually be a system that is heading towards practical viability. So we'll wrap up here in just a moment. Just 2 quick points that I want to make at the very end here. The first about why now, and the second about what are the other benefits of this sort of system. I think it's fair to ask why an electrically powered ammonia synthesis prototype that has not already emerged. Why isn't the world already making its ammonia using electricity if this is so promising in the way that I described? And a lot of this is because the price of electricity has fallen beyond what I think anyone could have imagined for renewable sources. Solar panels were $76 per watt in 1977. And just a few years ago, we hit a quarter, 25 cents per watt, and we're even lower than that now. We're getting to the point where the energy price for the electricity that goes into these chemical syntheses may no longer be the dominant factor. And that's a dramatic reversal from what techno-economic calculations used to look like just a few years ago. So this is one of the biggest drivers which we want to leverage in our own work. One more thing that I'll mention here is looking at the price of fertilizers globally. And I mentioned earlier that distributed manufacturing of fertilizers is important. And I want to give a little bit of data to support that. So what we have here is dollars per ton of urea. And urea is an ammonia-based fertilizer. On the far right-hand side, we have the international average price, which is about $200 per ton. And you can compare that to the price of urea in several countries in sub-Saharan Africa, in Burkina Faso, Cote d'Ivoire, Ghana, Mali, Nigeria, and Senegal. And you'll see that the price of urea is anywhere from 2 to 3 times the international average. The reason for this is because of poor infrastructure, which leads to high distribution costs. Those fertilizers cost about the same up until the point that they're brought to port, but it's that distribution from port to within these countries that adds a lot of cost because the infrastructure is not there. And so this is part of why we're really excited about developing electrified ammonia synthesis. But these are technologies which are modular since they involve lower temperatures and lower pressures, and that in turn could enable the synthesis of the ammonia close to where it's needed, overcoming these distribution challenges that have historically existed. So we come back now to what I shared much earlier in this presentation, this vision of being able to take CO2, nitrogen, and water to make all the chemicals and materials that we rely upon. We've talked about just ammonia here, which is an important part of this problem, but again, just one piece of that problem. So we're working in our lab on several other parts of this as well, learning how to convert CO2, which would otherwise be emitted, into a useful feedstock. So here, converting that CO2 into CO, and then making that into something that can then be further implemented in downstream reactions. And we're also working on epoxidation reactions, so ways in which water can be used as a sustainable source of oxygen atoms for chemical synthesis. This is a scheme which looks a lot like a water electrolyzer, where we're splitting water to make hydrogens and oxygens. But instead of recombining those oxygens to make O2 and just giving it up to the universe as something that has no value, why not use those oxygen atoms for useful chemical synthesis? And here we're showing how those oxygens can be used to epoxidize olefins. And those epoxides are used in diverse applications, all the way from polymers to antifreeze. So there's a lot of motivation for being able to decarbonize epoxide production, which today has the 5th largest CO2 footprint of any chemical that we produce. So 2 more examples of where we want to take this platform to impact diverse parts of chemical manufacturing. So with that, I'd like to thank our students and postdocs who have worked tirelessly on these problems. They've shown great passion and dedication, and I've learned so much from them as we work together to solve these problems. I'd like to specifically thank the National Science Foundation and the MIT Energy Initiative for funding our efforts on ammonia synthesis. And with that, would be happy to take your questions.
Thank you, Kartish. That was fantastic. And I think one of the great things about it is that you broke things down so that we could all understand, while at the same time bringing many of us back to our undergrad chemical engineering reaction and transport classes. So this has been wonderful. We're going to take questions, and we have several that are lining up now. So please continue to type them in. But just before that, I'm going to ask if people can look in their chat. I'd like to share a poll with you on future topics that we'd like to cover. And if you can sort of, you should see a poll floating in front of you right now. If you can sort of share your thoughts, that would be terrific. All right. And with that, I'm going to take the first question here, which is from Dan Crean. This is super exciting. Makes me proud to be a chemical engineer and to be an MIT alum. So that's a thumbs up. From Barbara Belt, is there also a market for all of the oxygen produced, or is it in excess of worldwide demand?
Yeah, really good question, Barbara. Yeah, so the oxygen that we produce at scale would place us in a regime where we're beyond what would be needed for worldwide demand. And so this is a case where that O2 we would consider as a waste product. We would just give it up to the world. And that's part of why we really want to try to find ways to do more useful reactions at the anode. So rather than going through all this effort to combine 2 O atoms to make that oxygen double bond, which is scientifically very difficult, why not use those O atoms for other synthesis processes? Why not use it for epoxidation, for O atom insertion into a CH bond to make a hydrocarbon into an alcohol? These are processes that we're working on in our lab and things that I hope will be able to give more techno-economic viability to these processes.
All right, the next one is related. Is this oxygen generated by making ammonia from water a potential hazard? Explosions from oxidation, for example.
Yeah, really important point. So yeah, it's something I didn't really describe in the presentation itself. So I'm glad you brought it up. So one of the really neat things about electrochemical reactors is that there's separation of the cathode and the anode. And this sort of spatial separation is really useful because it keeps us from having undesired contacting of the products of the cathode and the anode. So in a way, an electrochemical reactor can have a built-in separation. And what that means is that by keeping those streams separate, we can avoid many of the explosion hazards that would otherwise emerge. But of course, with the oxygen that we have here, one wants to vent that and dilute that into the atmosphere as effectively as possible to help avoid any unexpected hazards.
Excellent. Tom Griffin asks, do resistive losses translate to overpotential requirements? If so, it might be addressable by tweaking the chemistry. I might guess as you're describing right now. It mentions.
Yeah, fantastic point. So these resistive losses, we're working towards accounting where exactly they arise and how they arise. And there's this very sort of coarse perspective that one can take to say that some of it comes from electrolyte resistance and this other fraction comes from interfacial processes. But then there's a molecular picture behind those interfacial processes. I think this is sort of that beautiful boundary between chemical engineering and chemistry, which really in our department is very fluid. I think many of us effectively wear both those hats. So we're working on figuring out that molecular level mechanism that leads to these overpotentials, how to take shortcuts through the free energy landscape to get past these overpotentials. And those are things which I think will really contribute towards making this a more energy efficient process and perhaps something that could be practically used.
Excellent. Cody asks, how does your process compare on a CO2 footprint relative to the base case if you assume that electricity is generated from a more typical energy source such as coal or natural gas? The price of renewable electricity has dropped, but is the quantity available that we would need to replace most of the world's ammonia production?
Yeah, these questions at scale are essential. And so if we look first at the question of scale, we do in fact have enough renewable power. Now, of course, that renewable power is currently being used. So we would expect these to generally be new capacity that we need to bring online. And luckily the capacity that's being installed is just increasing at such a rapid rate that we believe that will be there. This question of what happens if instead of using renewable power, you just use grid power, I think is really important. We're actually undertaking a techno-economic study to answer just that question. I saw just some new data just a few days ago that we have put, it's starting to come together. And the first pass, which I'll give to you just as a preview, but hopefully we'll have something out in the open literature in a few months on this, is that it would have, one could perhaps reduce the CO2 footprint by half just by switching from the conventional process to a fully grid-powered electrified process, which to us is really promising because that half reduction could still have an enormous impact on the world without having to necessarily couple it to a new solar farm or to a new wind farm that would have to be created.
Excellent. Eric Reiner asks, what is the mechanism by which voltage shifts the equilibrium?
Yeah, so this is one of my favorite parts of electrochemistry, which is that voltage is this extremely potent force. There's a linear relationship between voltage and free energy. So that is the first sort of mathematical relationship that we hold in our minds. But there's a molecular picture behind that too. And the reason that linear relationship exists is that this is a charge moving through a voltage difference. And that voltage difference exists at the electrode-electrolyte interface. There's a very small region over nanometers of distance that we have a difference in voltage, and electrons are moving through it as they're going from the electrode to the electrolyte or in the opposite direction. And it's that journey of that electron through that interfacial voltage difference that then creates a proportional difference in the free energy, and hence this difference in equilibrium.
Excellent. Tom Griffin asks, why constrain the operating space to 25C? You can also make great gains in both smaller systems and lower pressure at, say, 100 to 250C.
Yep. So I think at the outset, part of the reason that we do this is that we like to make our lives a little more difficult. So there's a way in which we frame many of these paradigms to be as restrictive as possible. Whether that's, for instance, our paradigm of starting with just CO2, nitrogen, and water to do chemical synthesis is probably more restrictive than it needs to be, right? But it's something that by being restrictive and simple enables us to make progress in a very difficult problem. We've similarly constrained ourselves for the time being in our work so far to be at room temperature and ambient pressure, just because those systems will be most able to respond to intermittent power. And this is one of the biggest challenges of using renewable electricity for manufacturing. It's that the sun shines at times and doesn't, and the wind blows at times and doesn't. And if you want to do chemical manufacturing with it, ideally this should be a system that can start and stop in a heartbeat, so that there isn't any thermal inertia or pressure inertia built into the system. So that's part of why we've limited ourselves in this way. But I do actually agree that systems that are that operate at intermediate pressures and temperatures are useful. We're just starting to sketch out ideas in this space, and we're hoping to start to work in that arena, but it's something that we just haven't done yet.
All right. Bob Weiss asks, have you tried voltage pulsing to decrease the boundary layer effects?
Yeah, so we ourselves haven't, but there is actually a very recent report in the literature building off of some of our early results. So we're very excited to see the communities building off of things that we put out there. And another group just reported a couple of weeks ago that a pulsing scheme actually works. So that for us was really encouraging to see, one, they were able to reproduce our work and able to build on it, but that others are starting to make use of our results to work towards a day where this could actually be useful. But pulsing absolutely does help the system.
All right. Michael Manning, how much of the ammonia is used for fertilizer as opposed to chemical production?
Yeah, fertilizers are by far the largest application. And so when one looks at that transduction, we're first making nitrogen into ammonia. Part of that ammonia remains as ammonia, but some of it is then converted into nitrates and then combined, for instance, to make things like ammonium nitrate, also adding in things like sulfates and phosphates and other things. So there's this very diverse landscape that emerges. What that means is that we need to make not just nitrogen into ammonia, but also we're going to make nitrogen into nitrates, perhaps directly. And there are some really nice plasma-based efforts out in the community there that others who are much better experts on plasma-driven routes are developing. But then, in addition to that majority use for fertilizers, every application in which we see nitrogen in our everyday lives, whether that's in nylon, in amino acids, or whatever else we're using, so whether that's animal feed or the plastics that we interact with, that also comes from ammonia. So that carbon footprint's being inherited in a wide range of downstream products. So for that reason, our lab's also learning to take that ammonia that comes off of this process and make nitrogen carbon bonds. So you can imagine, doing CO2 reduction, making ethylene, and coupling that ethylene to this nitrogen to make, for instance, glycine. And that's one of the projects that we have underway in our lab to show that one can abiotically make an amino acid beginning with just these feedstocks, which would also be a first demonstration for an abiotic process.
Now that's exciting. Akim Weshan asks, it appears that you need additional hydrogen, which you were trying to avoid in your motivation.
Yeah, so the secondary, so I'll give a little background for this. So when we first started working on these processes in 2017, a new lab with a few grad students going on in an entirely new direction, we started by trying to do nitrogen reduction in a fully aqueous environment. So a single device, a single anode and cathode paired together, trying to reduce nitrogen in the presence of water to directly make use of those protons and electrons from water to make ammonia. And it turns out that chemistry is extremely difficult and maybe in blunter language, just doesn't work. And it turns out that it's just so much easier to reduce protons to make hydrogen than it is to take those protons and electrons and break the nitrogen triple bond at the same time to make ammonia. And that's part of why we've gravitated towards a 2-unit operation realization. One where we're first splitting the water to make hydrogen and oxygen, and then making use of that hydrogen in a secondary operation where there's no water present, and hence no competition or less competition from hydrogen evolution, and doing ammonia synthesis in a non-aqueous fashion. So that's something that we've advocated for pretty strongly in the community. Now, of course, I think there are breakthroughs on maybe on the 10-year timescale or 20-year timescale that could make a fully aqueous system possible. But I think this 2-step process is probably going to be what is useful on a shorter timescale.
Excellent. B. Mayarella asks, have you completed a techno-economic analysis, including conceptual design of a synthesis plant? What quantitative parameters must you achieve in the lab to be competitive?
Yeah, the techno-economics here are critical. So a lot of our early work that we undertook, we did without this sort of information from techno-economics, in part because the error bars were so large. We had no idea whether a certain parameter should be an order of magnitude bigger or an order of magnitude smaller. And since last year, now that we finally have a functioning prototype and one which works at reasonable rates, we've undertaken those techno-economic efforts. Those models are starting to get pretty mature. And I'll say just in a vague sense, perhaps, or numbers that are subject to change, but just to give you some idea that we think that an 80% Faraday efficiency, an energy efficiency of around 25%, and rates that are about an order of magnitude higher than we are today. If we hit all those things, we could actually be competitive in making ammonia. And so we're getting closer. You know, we started at 8% 3 years ago, and now we're at 50%. So we got to get that up to 80. Our rates have already gone up by 1 to 2 orders of magnitude. One more to go. And of course, energy efficiency, I shared a strategy for addressing. What that means is that this process, even though it may still take a number of years to be competitive, there are some markets where it may be competitive sooner rather than later. One example is in sub-Saharan Africa, where the prices are already very high. So this new technology could actually come in lower, even if it is still more expensive than the global average. And a second example, which we're interested in, is looking at the market for organic fertilizers. So while organic products generally are viewed in a very positive light, it turns out that the fertilizers that are used for producing organic produce are ones which actually have a pretty large carbon footprint. So those are usually coming from animal droppings. And the animal droppings, of course, have methane emissions and all sorts of things behind them. And that's how one gets organic certification. Those fertilizers actually cost 5 times what typical ammonia does. So organic certified fertilizers are 5 times more expensive. What we want to work towards is a future where fertilizers like ammonia are made from just air and water instead. Much cleaner process without the CO2 emissions, one which perhaps also lines up with certain segments of the market, consumers who want to be vegan or vegetarian and not be using animal products to produce things that don't involve animals to begin with, like agriculture. So there's an opportunity there, I think, but it's an extremely hard challenge, one that's going to require scientists working with policymakers, because these are guidelines that the USDA sets as to what is organic and what is not organic. And right now, it just turns out that the regulations are such that if I were to build a plant that takes air and water and makes ammonia, it would break the organic certification. So there are clear problems in the organic certification that need to be solved, but I think the sort of collaborations that we have at MIT could put us on a path towards being able to change those regulations.
Excellent. We have so many questions. Here's one. Critical to using cheap solar is running intermittently, i.e. only for 68 hours per day. Will the infrastructure be inexpensive enough to be idle for 2/3 of a day?
Yes, this is what we call a capacity factor problem. So one in the techno-economics needs to introduce a fraction that accounts for how often the equipment is actually used. So in our techno-economics, we're introducing a factor of 0.25. So we're assuming a quarter of the day we're getting solar and wind to be usefully used. Now it turns out one can actually up that capacity factor quite a bit by proper coupling of solar and wind. That as long as the wind is blowing or the sun is shining, you can make use of things at more times of the day. So there are actually certain climates and parts of the world that have higher capacity factors, but it absolutely drives what the question was asking for, which is that there is still room for reducing the cost of capital equipment such that these technologies can be practiced in a more diverse set of geographic regions rather than a narrower set, which happen to have higher capacity factors due to their natural way in which they receive sunlight or wind.
All right. And how do you feel about your demonstrated current density of 15 milliamps per centimeter squared? I believe that many electrochemical cells, hydrolysis, chlor-alkali operate at much higher current densities, lower capital costs. That from David Steckler.
Yeah, so the current density absolutely needs to go up by, we think, about another order of magnitude. When we started in this problem, the record current densities were hundreds of microamps, and we luckily have gotten that up to around this 10 to 15 milliamps range, which we were doing cartwheels on the day that happened. But we still know, we're still humbled by the fact that we have another order or so to go. So this needs to cross about 100 milliamps per centimeter squared to be something that, say, a startup or a large player in the space of ammonia could actually make use of to do something. And until then, it's a laboratory endeavor, but we think that we have several tricks up our sleeve and new ideas and things we've been sketching on our digital whiteboards even recently that we think could put us on a path towards solving it. But of course, these are high risk endeavors, so we should always be prepared to encounter failure along the way. But just knowing that there's nothing fundamental stopping us from doing that.
Excellent. We have a discussion about lithium from Gabriel Abgarinos. With demand for lithium batteries up for batteries, is there a limitation of affordable low-cost lithium as a catalyst? And then there's a comment about that from John Kavazanjian. But we'd love to hear your thought about the use of lithium.
Yeah, so one thing that we benefit from here certainly is that the lithium is used in a catalytic fashion, especially in our process where it is continuously turning over. So it's something that isn't held up in the same way that it is, for instance, in a lithium ion battery, where if you want to hold charge, then you're forced to wait in a charged state, and that lithium is stoichiometrically tied up. So there are differences in use and hopefully much less use. But these are the sort of important techno-economic considerations that one needs to make. Are there other metals that could perhaps do this? That's something we've thought a lot about. Why not sodium? Why not potassium? There are very interesting fundamental questions there about why lithium breaks the nitrogen triple bond while sodium and potassium can't. But that understanding could put us on a path towards finding alternative systems as well down the road.
All right. From Hugh James, when do you believe your research will produce a commercializable process, and how do you see this occurring? Entrepreneurial startup, undertaken by an existing fertilizer company, or some other approach?
Yeah, our students, I think, have a lot of entrepreneurial excitement, as I do as well. I'm surrounded in my family, my wife, and others who are working on startups, and so I feel like I live and breathe this over the dinner table in terms of thinking about how these sorts of things could be translated. So I think we do want to make that effort. I think many conversations that I've had with my colleagues, including Bob Langer and others who have made many startups, have made clear to me that even though that excitement can be there, it's just so important to de-risk as much as possible before taking that first step. And so I've really taken that advice to heart for us to try to be as patient as possible until the numbers make sense to push something like this out. So that opportunity could emerge perhaps in a few years for the specific technology that I described here. There are other technologies that are a bit different than what I described today that may even be ready on a shorter timescale, perhaps next year. But there are different pieces of this, I think many of which are probably best served by a small, nimble entity, but others of which cannot be implemented except at scale. And there we really benefit from collaborations and work with much larger players who can actually deploy the needed capital to have a dent on this problem at a worldwide scale.
Excellent. Maybe a related question from Howard Klee is, how would you expect to get economies of scale with electrochemical cells?
Yeah, the scaling here to me is one of the most fascinating problems. So a thermochemical process scales with a larger exponent. So it tends to scale closer to volumetric just because of the way that a vat can be made bigger and the way that compressors and heating of large reactors scales. Electrochemical processes scale with a smaller exponent. Intuitively, it's closer to being two-dimensional since it's an aerial process. I think at the outset, that may seem rather daunting. And what it means is that we really need to make use of modularity in order to bring out the full benefits and also seek benefits from that modularity in terms of reduction in distribution cost. And those are things that really can help make these processes more competitive. I'll also just mention though on the side that, these sort of scaling arguments that I just mentioned were used maybe 30 years ago to indicate that lithium-ion batteries would never be competitive for storing the world's energy because they also scale two-dimensionally. But we're seeing, that it's a very competitive landscape now. The jury's still out as to whether lithium-ion batteries will be good for grid-scale storage. But if one wants to implement a process today, it's hard to think of an alternative that's much more competitive than that. So there is a way in which even these two-dimensionally scaling technologies are cutting into traditional three-dimensionally scaling technologies. And that's something that we're going to continue to watch and understand and bring meaning to in a fundamental way, but in a practical way as well.
Excellent. We're going to take one last question, but before we do, I have one last poll for the audience just to get your opinion. I know there are people from many different fields on the conference right now, and we'd appreciate your thoughts about what we do with future programs. So if you can fill that out, then we will take the last question. And I will say we've had excellent questions, over 30. I can't, actually it looks like 40 or so questions. And it's hard to sort out which ones to ask, but I think the last one maybe, would it be from James Swartz, would it be economically feasible to store hydrogen and oxygen from the electrolyzer when the sun is shining and then use fuel cells when it is not, and otherwise have this fully cyclical system?
Yeah, this is essential. So the techno-economic model that we're building actually allows for storage of hydrogen and for the deployment of batteries as well, for storing that energy before it's used. So this implementation of storage to figure out, is it cheaper just to let the capital equipment sit idle when it's not needed? Or is it cheaper to implement energy storage and have a constant utilization of the capital equipment is very much a part of our big picture. And so for that, I don't have a clear answer just yet, but hopefully the study that we'll be able to get out sometime next year will actually have a quantitative answer to that question.
Well, fascinating, Kartish. We'll all be watching to see all of the developments coming out of your lab. And I know that we'll all benefit from these technologies. It's very exciting to see what you're doing with sustainability. And thank you to all of the alumni and visitors who came today. Let's thank Kartish one last time. And I'd like to wish everyone a wonderful and warm holiday.
A big thank you to Paula and to everyone who helped to organize this, and especially to our alumni. This has been one of the most engaging and invigorating discussions I've had in a long time. So really thank you all for coming out and thinking so deeply about our work.
Thank you, everyone.